Okay, good morning everybody. So here I'll be just sharing some of the latest things what we are doing with the MVAPICH project. Some of you might be familiar with that. If not, I'll be introducing it very soon. So this is a chart most of you must be familiar at this conference. This is the top 500 trend. So here you will see that this is the #1 system. Again, like these are all the numbers from the November ranking. Tomorrow morning we'll get a fresh set of charts. So here we see like the #1 system is the Tiahne-2, and I think that will still be maintained, I believe, in tomorrow's ranking. And then of course the community is aiming for 100 petaflop systems in the next few years, but the goal is to really reach the Exaflop system. And originally the target was 2018, but it is gradually moving around, and people feel that in the year of 2020 or 2022, we'll have some kind of an Exaflop systems in somewhere in the earth. Okay. So if you take a look at this, all these systems, an interesting trend, you will be seeing these commodity clusters. And these again, the data is taken from the top 500 list. If you see very in the early days, these were only the big iron machines, but clusters have become very common, and these days almost like 83 to 85% of the top 500 systems are clusters. And in those commodity clusters, if you see the main three ingredients are like multi-core processors, and then these high-performance networks, InfiniBand, most of you must be familiar here, and then the accelerators coming from the GPU side or from the Intel MIC side. So all these, the top clusters, if you see like Tiahne-1A or Tiahne-2, Titan or Stampede, all of them share the similar kind of architecture, multi-core, many-core, and then the accelerators. And here you see like in those clusters again, based on again the November 2013 ranking, we have like 207 clusters in InfiniBand, and the #1, the largest one is actually here, the TAC Stampede system. If some of you must be knowing, it has all the three ingredients I talked earlier, like the InfiniBand, multi-core, and also the Intel MIC, which is the many-core. And this system has almost 500,000 cores. So the question is, when these systems are being deployed, the question is how we are going to program these systems. Okay, and then there we come to these programming models, and most of you must be familiar with the distributed memory programming model, which is the standard message passing interface. There is of course the shared memory model, but that only scales to some number of cores. Most of the time this is within the node, not across the node. Some organizations have been able to scale to a set of nodes, but not very massive manner. But the new thing which is coming, and I'll be talking more about this, is the partition global address space, or called PGAS. So which is basically like a logical abstraction of memory across the set of node, and you provide some simple abstractions to do get and put kind of operations. So from any process you should be able to read and write to somebody else's memory, and that actually has lightweight one-sided communication, and the biggest advantage is to express irregular communication. Okay, and as we go on, we'll see the MPI is good for regular communication, or stencil, or some collectives, those kind of things. But when communications become very irregular, if you have access to a shared memory paradigm, that actually helps a lot, not only to write the program easier manner, but also to have a very good load balancing. So there are different approaches in the community. People have been working the language-based UPC, Core Fortran, X10, also library-based model, OpenSHMEM, global arrays, and Chapel. I'll focus on these two, one from each category, like UPC and OpenSHMEM, as we go along. So not only this PGAS is coming and MPI has been there, but now there is a growing interest to combine these two models, MPI plus PGAS. Okay, so the question here is like, as we go into this Exascale area, we will see that the machines will have hierarchical nature. So that means within the node we have shared memory, across the node we have no more shared memory, but within the server we might be able to get access to some shared memory. So like this, we'll have hierarchical architecture. So people have been thinking to have MPI across the address spaces and then PGAS within an address space, because MPI is good at moving data, and within that address space, MPI can actually operate with other shared memory programming models. And both these models can actually coexist with OpenMP. Sometimes people get confused saying we are trying to replace OpenMP. Now, OpenMP is for offloading computation on different threads across the different processes, but here we are talking about communication. The communication we can actually mix and match both with MPI as well as PGAS, and I'll show some concrete examples towards the end of this talk. And at the same time, you will see that when people are writing very large-scale applications, you will see that the applications have kernels with a different communication pattern. So let's say I have 10 important modules in the application. Some modules might have regular communication, some modules might have irregular communication. And so the question is, can they benefit from different models? And of course, you can say that, yeah, if the program is not good, I can rewrite. But as you will see that as HPC systems are becoming very large, these applications are also becoming very larger, and it's very difficult to rewrite all of those from taking from one model to the other model. So then the question is, can we port some critical kernels to the desired model? So let me illustrate it here. So think of like an application, it has some n number of kernels, and in the end you see that this application is not scaling. Now if you go inside and then try to analyze, then you might see that, oh, let's say only few kernels, they are not scaling. And they might have irregular communications, they might have some load balance problems, and might be, let's say that it was written with MPI, and you are having very hard time to get the best performance here. So the question is, can we change those to PGAS? Okay, and at the same time, the other modules or the kernels will still remain MPI. So it is a mixed programming now. You should be able to have that applications running with both MPI and PGAS. And this is what actually, in fact, there's a lot of focus in the Exascale roadmap saying this is the hybrid programming is a practical way to program Exascale system. So we can take advantage of distributed memory model as well as shared memory model. Again, I'll show some examples in our MVAPICH2-X project, how you can actually try to achieve this on your system. So if you take all this broader look, now try to ask the question, how do we really design the software libraries for the multi-petaflop systems and Exaflop systems? So you will come up with an answer like this. So if you see here at the bottom, we have these are the components I call like a supply side component. So that means we have multi-core, many-core architectures, all different networking technologies, and also all different accelerators like NVIDIA and MIC. And on the top, we have all these applications or application kernels. And we want the best performance and scalability at this layer. So that means we need to take all the performance and put it here. But of course, these applications are written with some kind of middleware, and they are written with some kind of programming models. So it could be MPI or PGAS or UPC, OpenSHMEM, or you can think of CUDA, OpenSCC. So you name any of these things. Even for big data and all, you can think of Hadoop, MapReduce and all sitting there. So now the challenge is, how do we take the performance and scalability from here to the programming layers? And this is where the role of the communication library or the runtime comes in. Okay, the most matured you can design the communication library and runtime to harness all the performance, then you will see that the implementation of those programming models will be very good, and then the applications can take advantage of it. And of course, within the communication runtime, there are all different components, like how do we handle good point-to-point communications, like two-sided, one-sided? How do we handle collectives? For example, broadcast, reduce, all-to-all, etc., synchronization and locks, I/O file systems, and fault tolerance. So these are all the challenges you need to bring within the communication library. Of course, the systems are being very complicated these days. So if you just take a look at it in a layered manner, things may not be the best possible solution you may not get. So there is a lot of activities taking place in terms of co-designing. So that means we are trying to run across the layers, and I'll show you some examples, especially for like non-blocking collectives, which is being proposed recently in the MPI-3 standard, and how you can take that and modify the application, and as well as the underlying runtime with some offload mechanisms, and you try to get the maximum performance. So there are a lot of focus on these co-designing opportunities, focusing on performance, scalability, as well as fault resilience. So now let's say you come up with a wish list saying, let's say these Exascale systems are coming, and we'll have some kind of a model, say MPI+X. So X is not defined here. Again, X could be PGAS or some other variations. In general, people are talking about MPI+X. So you will come up with a wish list like this. Okay. For example, how do we achieve scalability to million to billion processors? Of course, we need very good performance, inter-node and intra-node. And the other challenge is how do you design these runtimes with extremely minimum memory footprint? Because as the system sizes are increasing, the library themselves are consuming more memory. But at the same time, if you see in the multi-core and many-core perspective, the amount of memory per core is reducing. So how do you balance these things so that you want to design a good library, but it should take extremely memory footprint, and that is also a big challenge. And then how do you balance intra-node and inter-node communication? Because as of now, like you know, each of the node these days have 32 or 48 cores, and very soon we'll see 256,000 cores. So there is a lot of communication happening within the node. So you need to really balance the communication within the node and across the node. And then, so there are some different kinds of techniques people are proposing: endpoints, efficient multi-threading, and then of course the support for GPGPUs and accelerators, because these are becoming an integral components of the system, and they cannot be thought of like second-class citizen. You need to take them in an integrated manner to design your library and runtime. And then, of course, the collective communication, especially in the scientific computing, as you know, that has a big place. If you don't accelerate your collective operations, you get choked down because of that. And then there are a lot of different kinds of solutions people are proposing: offload, non-blocking, topology-aware, power-aware, etc. And then, of course, fault tolerance, resiliency, that is important because as we are heading into Exascale, these are commodity components, and they are going to fail. So how do we handle the fault tolerance? And then, of course, the quality of service support. That is like if different jobs are running, how do you provide quality of service across the different jobs? That is also a challenge. And then finally, this kind of newer programming models like hybrid MPI-PGAS programming, how do you achieve those? So these are the kind of a broad challenges we need to do. So we at OSU have been working on this almost from like 2001. When the InfiniBand started. So these projects have been like almost 13 years long now. The project is the MVAPICH project. We had actually the first open source software distribution with the MPI-1 standard in the supercomputing 2002. And then since then, we have been continuously enhancing it. The latest have all these MPI 2.2 as well as the latest MPI-3 standard. And then since 2 years back, we introduced this MVAPICH2-X. I'll go into more details, which combines both MPI and PGAS. Using this stack, you should be able to program using MPI with UPC, with OpenSHMEM, or any combinations. You can combine MPI and OpenSHMEM, MPI, UPC. So it is one stack for everybody. So you should be able to use your favorite programming model using the stack and then see how the applications can be redesigned. And then for the last several years, we have also been adding support from the GPGPUs and MIC in an integrated manner. I'll talk a little bit about that in the later slides. And steadily, like it has been gaining a lot of acceptance. Nowadays, more than 2,000 organizations in 72 countries are using this. And not only that, these packages are now empowering a lot of these top 500 clusters in production environment, even though it's a project we started from academia, but it's actually a production software, and it's running on these, like the Stampede is the largest one with 500,000 cores, and all these other large-scale systems like Subami, Pleiades, Kinland, all these large-scale systems use this stack. So what I'll try to do is like trying to go into a little bit of details of these stacks, and then trying to say, okay, how we are trying to achieve those kind of objectives I outlined in the MPI+X for Exascale, and where we are and what we have done. I'll try to show some performance numbers, and at the same time, I'll also try to outline some of the challenges. Now, we just made a release just 2 days back. If some of you are on our mailing list, you would have seen this. This is the GA release for the MVAPICH2 2.0 and MVAPICH2-X 2.0. So mostly it has a lot of MPI-3 support. The MPI-3, the remote memory access support for non-blocking collectives. MPI-3 also has something called MPI-T, that is the MPI tools interface. You can actually use it to get a lot of information from MPI library, and at the same time control the MPI library. So this is the new direction which is emerging, so that you can drive your MPI library with your desired behavior. So those kind of interface supports have been provided. And then also for the intra-node, like within the node, as I said, like the nodes are becoming fatter, you need a lot of communication happening within the node, and you need to optimize that. So there is a newer, earlier we used to have a module called LIMIC. Some of you might have heard of that we started almost like 7-8 years back as a newer kernel module, but all those concepts have gradually gone to the Linux stack. So now there is a standard module called cross memory attach with exactly similar functionality. So we have that with also optimization of collectives, large memory transfer, and also this is the reduced memory footprint. I'll talk about a little bit how you can use different kinds of transports, the InfiniBand transports like RC, XRC, and UD. But not only that, the very latest, which is the called DCT, direct connect transport. I'll show you some numbers with that. And of course, as the system sizes are becoming larger, there is always a big challenge on how do you do job startup? How do you improve it? That itself becomes a big challenge. I mean, just if you're on a 500,000 course, if the job takes like 30 minutes to come up, I mean, that's not good. So we are continuously over the last 14 years trying to reduce this job startup time with good mechanisms. And of course, as newer and better models keep on coming, we try to keep on looking at optimization techniques to optimize collective and do various kind of tunings for all different kinds of platforms and adapters. And similar kind of things that goes also into the MVAPICH2-X side, not only for the MPI, but also for the PGAS, UPC and OpenSHMEM. So this latest version has all the latest things, like not only MPI-3 from the MPI side, but also the latest version of UPC, latest version of OpenSHMEM, and any combination of those. So let me go into some of the details here. So first I'll try to focus on the scalability aspect, go into collectives, then support for GPGPUs, Intel MICs, fault tolerance, and hybrid programming. So those are the kind of performance also. So this chart actually I show in a lot of presentation here. Actually it shows how the things have been evolving over the years. So this is the performance of MVAPICH2 across all different kinds of InfiniBand adapters and platforms. Okay, so here for example like QLogic, DDR, QDR, from Mellanox we have ConnectX, ConnectX2, ConnectX3, and then the ConnectIB, and then ConnectIB also like whether it is associated with like the SanDisk's platform or the IBP's platform. And here it shows like the latency chart. So this is like half of the round trip, node to node. So here you will see that over the years we are continuously decreasing. So these days we are below 1 microsecond. So you can do from node to node, the communication time is less than 1 microsecond. And then this is the latency for large messages. Of course, the bandwidth matters here. So this is the IB bridge with ConnectIB dual FDR. That gives the best performance for large messages. And these are the unidirectional bandwidth and bidirectional bandwidth. So the left hand is unidirectional. That's you are pumping data from one node to the other node. So here you will see that over the years, things have been improving. And the latest IB bridge with ConnectIB dual FDR is 12.8 gigabytes per second. So if you multiply by 8, it's 100 gigabits per second. You can achieve that in the commodity network. And then the bidirectional bandwidth, both sides are communicating with each other. So we are very close to 25 gigabytes per second or 200 gigabits per second. So that's the kind of performance you get these days with commodity systems with InfiniBand. Now, not only the node-to-node communication matters, but as I said, like there is a lot of, with the multi-core era, a lot of communications are happening within the node. So you also need to optimize those, otherwise you don't get the performance. And again, once again, over the years, we continuously optimize this communication. I think now we have put the 4th generation design, the shared memory designs. So here you will see that this is again the similar kind of latency, but this is intra-socket. So that means the cores which are sitting in the socket, within a socket, and to do MPI communication. So we can give you 180 nanoseconds. Okay, so we are now into the nanoseconds region. From MPI latency, we get around 180 nanoseconds, and then the inter-socket it's around 450 nanosecond. So this is for short messages. Now for the large messages, so this is where if you just use the basic shared memory, you don't get very good performance, but this is where the kernel-based modules come in. And as I was telling earlier, we had the module called LIMIC. This was designed in our group several years back. But a lot of these concepts have now gone into the cross-memory attach, which are the standard calls on any Linux kernel. So with that, you will see that you will be able to get high bandwidth for large message transfer. So the MVAPICH2 stack has all these things. So if you are trying to actually use on your platform, so I'll strongly encourage you to turn on either CMA or LIMIC so that you get very good performance with large message sizes. And now this is the new MPI-3. As I said, MPI-3 has this remote memory access. Of course, in the MPI domain, one-sided communication has been a challenge. MPI-2 standard had some of those things. In fact, we had that support, but that had a lot of overhead. And then those overheads have been trying to be reduced in the MPI-3. So we have a full support for MPI-3. So this is some sample numbers. Let's say you have a get and put. The internode get and put we are able to do in 1.56 microsecond, and get we are able to do 2.4 microseconds. And then this is intra-socket. We are able to get it very low, like 0.08 microseconds, like 80 nanoseconds. And then the bandwidth-wise, here we are able to again match with the network speed here, and also this is within the node we get similar to the two-sided. Now coming to the memory footprint, so this has been a big issue, as I was indicating, and this is InfiniBand Consortium has been trying to handle that for some time, and from the MVAPICH stack point of view, we are also trying to take advantage of similar kind of things. So many of you know, like InfiniBand standard has this RC, which is the reliable connection, but then if you go through the reliable connection, as you keep on increasing the number of connections, the memory footprint keeps on increasing, and then this extended RC was introduced, XRC, and that reduces here significantly, and it shows this like this, the reduction in communication time, memory footprint, and the right hand side, this is a 1,000 core experiments on NAMD. You will see, in fact, you also gain a little bit in the performance. And since for the last several years, we have actually combined many of these things, like saying UD, hybrid, and RC. So they are actually combined. We have a hybrid mode. It's like a hybrid car. I give the examples, like you want to get the best mileage with the minimum gas consumption. So same thing we have done within the MPI stack. You get the best performance with the minimum memory footprint. Okay, so if you go through the MVAPICH stack, you will see you can run your application with UD mode, pure UD mode, or pure hybrid mode, and it has some, like internally we have some parameters so that it learns, or it learns the behavior, the communication behavior of the application, and then appropriately decides when to use UD and when to use RC. So once again, if you're running very large-scale applications, I'll try to suggest you to go into these modes, because the standard RC mode, you may get choked, and you may get messages saying there are no memory, or you cannot run large-scale applications. So all these things have been there in our stack. And then this is the newest thing. What we have done is the DCT. We have actually a research paper presentation here on Wednesday. So I'll strongly encourage you people to attend that. So I'll not go into very details here. But this is the new direct dynamic connect transport from Mellanox, which is a constant connection cost, like 1 QP per any peer. And with that, you have full feature set like RDMA, atomics, etc. And then these are some terminologies, like there is a DC target, then the messages are routed through that. You need some DC key. But let me show you some sample numbers here. So this is trying to show a memory footprint all-to-all. As you know, all-to-all communication up to 640 processes. And it's trying to show the connection memory. So this line is the RC. This is the UD. This is the XRC. In fact, this is like very low, so it doesn't come. And then this green is the DC pool. So here, let's say, see for the 640 processes. So compared to like RC takes like a 97 this is a relative thing, so compared to 97 units, so here it is only 2 units. So you significantly reduce the connection memory requirement with the DC. And here, not only like you reduce the memory footprint, also you see some benefits in the performance. So this is the NAMD running on a 620 processes. One node was bad, so we are not able to go to 640. But see the relative timing. So this is the DC pool. The new design is able to actually give you the benefits. And that is the newer way to proceed with this kind of transport. You should be able to really scale to a large scale system with reduced memory footprint and also get the maximum benefit in your execution time. So now let me switch to the little bit onto the collective communication angle. So those are all the point I showed. So the collective communication, again, InfiniBand has hardware multicast. So with the through hardware multicast, you should be able to send the data to all the nodes. And these are the numbers taken from the tag Stampede, all the CPU cores. These 102,000 cores. And now if you see the default, if you let's say do this is a MPI B-cast. And by default, if you do through software like a k-nomial tree or binary tree, this is the kind of performance you'll get around 20-25 microseconds. But if you switch to the hardware multicast, you get it around 5 microseconds. So in the 5 microseconds, you should be able to cover 102,000 cores. So that is a very fast operation you can do here. The similar benefits you see on the large messages. But as you know, like this hardware multicast is only valid in the InfiniBand for UD, and it is only valid for up to 2K MTU. And after that, you may need to copy and then add reliability. So that's why for very large messages, you win, but that's not in a big manner as the small messages. So if your application has a lot of small messages, I'll again strongly suggest you to turn on. MVAPICH2 stack has this UD multicast support, so you should be able to turn on. And a lot of other collectives like reduce, all reduce, etc. also depend on this feature. So if you turn on, you should be able to see good benefits. And this is like the similar kind of things shown in a different manner, like a 16-byte message. As the system size is scaling, you will see this is the software-based design and this is the hardware multicast. So you almost remain the same as you keep on increasing the system size. And even for the large messages, 32 kilobytes, you see the similar kind of a constant latency. So then this focus is these days a lot of focus on these non-blocking collectives. So the broad idea here is that the earlier MPI standard had all the collectives as blocking. So that means if we do a all-to-all or MPI B-cast, all the processes wait for the results to finish, okay, and then continue. So obviously that has some limitation because you are not able to overlap computation with communication, and you don't get very good scalability. So MPI-3 standard introduced these non-blocking collectives. So just like the point-to-point, you have I-send compared to send, which is like a non-blocking point-to-point. So similarly, you can do a non-blocking collectives. That means I all-to-all, I B-cast, I reduce, and all. So that means if you have applications and if you have computations to be done, so what you should be doing is you initiate a collective, but don't wait for the results. If you have some computation, you proceed, and then after you finish that, you come back and check that whether the results of the collectives are ready, and then you proceed. And that actually allows you to do both overlap of computation and communication. So with that concept, what we have done here is that not only we have the non-blocking operations, but as you know, many of these Mellanox adapters actually provide collective offload. This is the CUDA-direct mechanism from Mellanox. So then what we have done is we take non-blocking applications and then non-blocking collectives with the CUDA-direct support. But to really see the benefits, you have to modify the application. So that is the big challenge, because these will not just run on the existing applications. Because even though you just introduce non-blocking collectives, but if the application was written with blocking in mind, if you just replace with non-blocking, you may see the similar performance, but you will not extract the real overlap. So what we did is we actually worked with some application scientists here. So this is like a P3D FFT. So we took all-to-all, and we modified that code and modified the all-to-all, non-blocking all-to-all, and then put them together. And then here you see It's like you get around 17% benefit. This is an application from Lawrence Livermore National Lab, the PCM, pre-conjugate gradient solver. So here we get 21%. Even HPL, the one which gets used to rank all the machines. So there also we get almost like a 4.5% benefit. So these are actually, these schemes illustrate that how the non-working collectives can actually be utilized together with CUDA-Direct to get the best performance on the next generation systems. The next challenge is the topology. As the systems are becoming very complex, so the question is how dynamically we can detect the topology and that take the topology information into collectives, into point-to-point, into rank reordering. So a lot of opportunities exist here. So here I am trying to show like a topology-aware placement. Okay, so if you think on a large-scale system, let's say I got a 4,000 core allocation, and you launch a 4,000 core job, MPI job, but the question is, are they properly being placed? Okay, so that means by default, like the rank 0 goes to core 0, rank 1 goes to core 1. That is a very simple scheme, but it doesn't take the topology into account or the communication information or exchange into account. So what we have done here, this is a study, we had a paper at SC 12. It got the best paper and best student paper finalist nomination. So what we have done here is that through OpenSHMEM, we directly discover the network topology. So as the job is being launched, we detect the topology information, and then from the application through some hints, we can get the communication characteristics, and then trying to match that, saying which rank goes where. Okay, and that's what is being shown here. This is the application milk. This was done on the Ranger, which was the prior to Stampede at TAG. So what this is trying to show, this red line is showing the intra-node communication. The green line is like 1 hop communication, 3 hops, 5 hops, 7 hops. So here we saw that not all communications are happening within the node. There are a lot of 3 hops, a lot of 5 hops, 7 hops communication, and these are the communications which go through contention from other jobs. And through this rank reordering, we are able to actually optimize, and then here we see this compared to this, you will see the intra-node communication is very high here, and then we are able to reduce these 3 hops, 5 hops, and 7 hops, and in the end, on a 2K job, you will see 15% reduction in execution time. Okay, so these are the kind of tricks we need to play for the next generation systems with the MPI stack, so that we actually take the topology into account to get the best performance and scalability. So then there is a lot of focus these days on power-aware collectives. Here again, the question is like, how do we design these collectives so that not only you get the best performance but reduction in power? So here we have done some schemes broadly, like there are a lot of DVFS schemes together with RAPL interface are coming. You can actually control the behavior of the processes. So here we designed an all-to-all scheme trying to do some orchestration in doing this all-to-all collective so that everybody, all the cores are not alive and then just doing the polling. And by doing a good orchestration, we are able to reduce the power by 32%, but performance may get hit a little bit. So you have some flexibility in how do you manage, how do you balance the performance and the power. So then let's move to the GPGPU stuff. So as there is a lot of activities taking place in the GPGPUs for the last several years, we actually introduced something called CUDA-aware MPI. Earlier the MPIs were not CUDA-aware, people are just doing CUDA, but we took it within the MPI stack so that an MPI designer doesn't have even to touch CUDA. So just like you are doing MPI send and receive from the host memory, you can do it from the GPU memory. So that support has been there. Since like earlier CUDA 4, there were a lot of copies were happening. After CUDA 4, there was only one copy, and very recently this GPUDirect RDMA has come, which Paul indicated, so I'll go into a little bit more on that. So as the GPU technology have been evolving in our MVAPICH2 stack, we have been providing continuous support for that, for the point-to-point communication, for GPU to GPU, GPU to host, host to GPU. We also take care of the intra-node point-to-point communication, take advantage of CUDA IPC, optimize and tune collectives, as well as data types. So in parallel, like just like we are progressing with the host and network, we also take the GPU technology into account and then provide all the features into our stack. So now this is the new GPUDirect which has come. So that means you can actually send data from GPU memory over the InfiniBand. So if two of these are connected with the same PCI PCI interface, you should be able to move data back and forth. But there is still some bottleneck here. This shows some performance like P2P write. So that means getting data from network and writing is good, both for Sandy Breeze and Ivy Breeze. But reading the data is not good. That is a poor performance. So here we have done some kind of an hybrid design. This is a limitation from the chipset, nothing to do with GPU or InfiniBand. It's the Intel's chipset has this limitation. So to alleviate that, we have a combined scheme. For short messages, we take it through network. For large messages, we still go through the memory and come back. Okay, so that gives the best performance. So here you will see these are the sample numbers compared to the basic one. If the GDR, this is the GPUDirect, you almost reduce the small message latency by 67%. So this is like 5.49 microsecond. You get similar kind of benefits in the large messages. And the bandwidth wise, you can push the bandwidth. So this is the bandwidth, higher the better. The small and medium messages, you get almost by a factor of 5x improvement. And here also you get the full network bandwidth. And bidirectional bandwidth, you get almost by 4.3x. And here it is with a dual rail, that is a connect IB. So with the connect IB and GDR, you get the best performance, like totally saturate the network back and forth. So these designs have been there. We have this MVAPICH2 2.0B GDR. Please feel free to download if you have not tried it. So these are all the requirements. You should download and you should run and get similar kind of performance. But that is the public release. Now we have been working for the last several months. These are all the very brand new results. We are closely working with NVIDIA folks to come up with two additional enhancements. This is called the MV2 GDR new. We have a loopback scheme. And then there is a fast copy scheme which Davide Rossotti from NVIDIA has designed. Now, together with that, these numbers were actually taken on Wilks. As Paul indicated, they have been very helpful to us. These are not publicly available packages, but they were willing to allow us to put all those libraries. We crash their systems, so we are the crashers for their system. But still, we'll be able to get all these numbers. So now see the performance, 3.5 microsecond. That is the best numbers we can have from GPU to GPU using GPUDirect RDMA. From one GPU going over the network to the other one. So that is the small message latency we see. And if you do that together with this, the HUMD Blue, this is an application again run on the Wilks. So now you can see the compared to the current release, which is the red line, this green and blue, we are able to boost performance by 47 to 48% for strong scaling mode. And for also weak scaling mode, we are able to push 53 to 56%. And then that is the two-sided operation. So now the question is, can we pass similar kind of performance to the one-sided? So what we have done now, this MPI-3 RMA on GPU buffers. Nobody else has this kind of designs. And see the numbers. It's less than 3 microsecond. 2.8 microsecond, we can send actually this is the put operation from one GPU to the other GPU, from GPU buffer to GPU buffer. And right hand side is showing the message rate. Again, we steadily improve for almost by a factor of 4 if you go to this kind of one-sided operations over the GPU buffers. So we are putting together all these things. In another few weeks, we'll see that you will have a new release here with all these designs. So you should be able to actually try to use it for your application and see how your applications can scale with the latest, not only the GPUDirect RDMA, but with this MVAPICH2 enhancement. So next, let me switch to Intel MIC. So that is the GPU side. The Intel MIC side also is progressing in a similar manner. As many of you know, like Intel proposes all different modes, like the offload mode, symmetric mode, coprocessor mode. So we have also been working trying to optimize MVAPICH2 stack for all these the Intel MIC. Now this picture actually shows the complexity. Here it shows like all the different places where MPI processes can run. Like across the host, across the PCI, the Intel mics, and that leads to a lot of these communication paths. Okay, I'm just quickly going over all these things. There are all these 11 possible paths in the MPI stack you need to optimize, okay, to get the best library, so that whatever Intel claims that, okay, all the symmetric mode, coprocessor mode, every mode will operate with the best performance. And that takes a lot of effort. So we have been continuously enhancing all these things. In fact, there is a version running on the TAG Stampede. If you have access to the TAG Stampede, you should be able to use that library. It's not publicly available yet, but we are continuously getting the feedback and making enhancement. So here is the same issues also exist. The chipset limitation, as we saw, like the reading is, this is the intra-socket, reading is poor, and across the socket, it's in fact very poor. Again, just go to 247 megabytes per second. That's the kind of performance you get. So this is the new design, what we have done. This is the MV2 and then this is the MV2 mic. So here we can reduce the latency, as well improve the performance significantly. This is the bandwidth, and both on the intra-socket and inter-socket. These are some application numbers. We get around 50% improvement, 16% improvement here. But not only the point-to-point matters, but the collectives. Now it becomes a much more bigger headache because all those paths are there and you are running a collective. So you need to come up with newer kinds of algorithms. So the previous generation algorithms are not good. So we had a paper presented last month at IPDPS. So here it shows like how you can re-enhance like an Allgather or Alltoal kind of things to get better performance. So once again, we are putting together all these new designs. So might be another month or so. You will see MVAPICH2 mic release is coming out. Now let me accelerate this a little bit. Brian is showing me time is running out. I'll skip the fault tolerance part, but let me go to the PGAS part. So here the idea is that, as I indicated, people are looking for not just MPI, but very good high-performance implementation of PGAS like UPC or OpenSHMEM. Or the question is, how do we combine them? And in order to do that, we have actually designed this MVAPICH2-X, which has been there for several years. So this is the MVAPICH2-X, which is a unified runtime. So that means that it's at the IB layer. It doesn't distinguish whether a message comes from MPI or UPC or OpenSHMEM. So it is a combined unified design with shared resources like all buffers, connections, etc. And on top of these, you can have pure MPI or pure UPC or pure OpenSHMEM or any combinations. Okay, so you should be able to use this stack to experiment with your favorite programming model and then see the benefits for your application. So here I'll show some sample numbers. So these are the OpenSHMEM collectives. So we are showing here MV2-XMEM and scalable SHMEM, also the OpenMPI SHMEM design. So we do very good in all these collectives. Here, this is some application-based evaluation. The similar trend we see here, like this is the MV2-XMEM. This is the orange line, which significantly does better compared to all these other stacks. Now this tries to show the combined effect. So we took two applications. One is the Graph 500 application here. This is typically run with MPI. So we have taken like some of the parts I mentioned earlier, some of the parts were not scaling, and we converted that into OpenSHMEM. And then combined these pieces together, and this was running on the unified runtime. And if you see here, this is on the TAG Stampede with 60,000 processes, we get almost factor of 13 improvement, okay, compared to the default MPI. Even to the best MPI also, we get almost like a 1.5x improvement here, and it shows very good, strong scalability, and also the weak scalability. Then recently we have taken another one application called SORT. So that is again a lot of people use in the scientific domain. The similar kind of things, the pure MPI was not scaling, and our hybrid version is able to give like on a 4 terabyte running on a 4K nodes. We can give you almost like a 51%, and the strong scalability we can give you 55%. So these are the kind of demonstration that you can actually combine these different programming models. As I mentioned earlier, like a lot of applications have regular and irregular communication. So how do you take the the different kinds of programming models to mix and match, and that's what is being shown here. So if you have such an application and you are not getting the performance, so I'll strongly again suggest you to use MVAPICH2-X, and then you should be able to get similar kind of performance on your system. So to conclude here, so we continuously, for the last decade, we have been monitoring very closely with the technology trend and putting newer kinds of designs into our MVAPICH2 and MVAPICH2-X stack. And we continue to do plan to extend that for the future years. So our next goal is to scale it to 1 million cores. Of course, I just showed the basic design with the DCT. There are a lot of advanced designs for point-to-point, RMA, collectives, so all those things we want to do. Then, of course, the newer kind of supports are coming in the CUDA 6.5, the Intel MIC, and all these non-blocking collectives. So we plan to continue. As the newer technology comes, you will see solutions coming out from the MVAPICH2 and MVAPICH2-X so that you can utilize this. So to conclude here, as I showed, like InfiniBand with the RDMA feature is getting momentum. As we are moving into Exascale, there are a lot of challenges, and I demonstrated how some of these solutions can be actually designed with MVAPICH2 and MVAPICH2-X. These are our standard sponsors, but I also want to acknowledge all my students and staff over the last decade. They have all contributed here. I just come give a talk, okay? But they are the heroes. The final thing, I just want to spend 1 minute here. Since last year, we got a lot of requests from the community to have an MVAPICH user group meeting. Okay, so to discuss all the issues and share the knowledge, we had a very good turnout last year, so we are now doing this year in August. So these are all the speakers who have lined up, our two keynote speakers, Dan from TAC and Darren from PNNL, as well as a lot of talks. And we are actually putting together a half-day tutorial purely on optimization and tuning, MVAPICH2, MVAPICH2-X, MVAPICH2 GDR for your platforms, how you tune. And also, we'll have a contributed presentation. So if you have any new results using MVAPICH2 and MVAPICH2-X and you would like to share, please submit your presentation. We have the deadline July 1st, so we'll have a 2.5-day event. So I'll strongly encourage you people to attend. So that will actually build a community with all the shared knowledge, so that everybody can learn from each other as we grow in the community. And last but not the least, I always show these slides. I always look for people. If you are students, staff here, you would like to come work in our group, you are always welcome. With that, I'll be happy to take few questions. Otherwise, I'll be here throughout the event, and I'll be happy to discuss things. Thank you.